guess I have a few messages. One of them is current AI is very bad in terms of how much it understands the world around us. Then I'll explain more specifically some of the things that I think are missing that at MILA we are working on. And then I have a few words about some things we're doing that have to do with beneficial AI, maybe not beneficial AGI yet. So, well, I don't need to spend much time to convince you that there's been huge progress in AI, in great part due to progress in deep learning. But maybe I want to mention that the neural nets of today are very different from the neural nets of the 90s, not just because of depth, but things like incorporating attention mechanisms, memory, being able to handle any data structure and not just vectors, and being able to generate data in a way that, in the 90s we had no clue how to do, or even until recently. And then, of course, lots of applications. This is the progress of generative models over 4 years, from 2014 to 2017. Okay, but if you want to be, honest about where we are, it's amazing how superficial and how shallow in a semantic sense the current models are, and you can see that in the kinds of mistakes they make. Of course, many of you know about adversarial examples that you're seeing here, and the fact that most industrial applications are really based on supervised learning, which require humans to define the high-level concepts that the machines are supposed to learn about. And the other thing maybe people realize a bit less is that if you look at the kinds of mistakes they make, not just with adversarial examples, but other kinds of more natural mistakes, you see that as soon as you take the current models out of their training distribution, they can fail in pretty bad ways. And one reason why this happens is because they rely on low-level. They tend to rely on low-level superficial properties, like here in the experiments we did in this paper last year, properties of the Fourier distribution, Fourier spectrum of the images, which can be manipulated in ways that humans will not even care about, but will completely screw up the classifiers. In natural language, you can also see lots of examples of failure, even with like the best, say, machine translation models or the best language models. For example, here you have an example of Google Translate I just picked recently from a cue coming from Doug Hofstadter. If you try to translate from English, in their house, everything comes in pairs. There's his car and her car, his towels and her towels, blah, blah, blah. In French, the translation is wrong because it's just basically translating his to ça and her to ça. And unfortunately, in French, it's the same word, and so it completely loses the meaning. And in French, you would have to change the actual structure of the sentence to get it right. So it's like these machines are very myopic, and they've basically learned little approximate rules that are all stuck together, but no overall understanding of what the sentence really means. You can also see this by looking at the performance of these systems when you ask pointy questions about the meaning. Of course, when you measure like statistical performance in tasks like machine translation, it looks good. In fact, some people claim, I've just read something recently. We got machine translation reached human level accuracy. This is bullshit, right? Because, of course, in numbers, or even like computer vision, right? We have not reached human level computer vision in spite of what you might read. Because, of course, if you take a data set and you just count how many errors, it looks good. But then if you focus on the errors and you see the kinds of errors that are made, they're very different from the ones humans make. So, for example, if you try to train a system to answer questions about like what is they referring to in these sentences, humans will get it 100% accurate because they understand the meaning behind the words. So the women stopped taking pills because they were pregnant or carcinogenic. Then, of course, they refers to women or pills. And current state-of-the-art systems that are based on deep learning, of course, do only barely better than chance. I mean, they're able to pick up some cues, but And in general, if you try to compare our best systems to babies, like 1-year-olds, 2-year-olds, 3-year-olds, our systems don't even have the sort of understanding of the world in terms of intuitive physics or intuitive psychology that small children have. Now, a bit more than a decade ago, Jan LeCun and I wrote this paper where we sort of laid out our objectives for deep learning in terms of the notion of disentangling the underlying factors which explain the data. And the idea is that if we can learn a hierarchy of representations where at the top level we really have figured out the important factors that explain the data, then we're going to get much better generalization because in that space you can learn new information much more easily. How to relate variables now becomes a very low-dimensional learning problem. More recently, I've come to realize that it's not just about learning which variables matter to explain the data, but also how these variables are related to each other, which could be in terms of thinking how the data was generated, or thinking about how to perform computation in a way that's going to be efficient. So there's a notion of disentangling computation as well, factorizing knowledge either in the generative sense or in the computational sense. And as I'll try to argue later, this has a lot to do with the ability of models to figure out causal structure in the world, something that we don't really know how to do yet. So, so this notion of disentangling representations, we elaborated a bit more in a 2013 review paper with Aaron Crowell and Pascal Vincent. And the general idea was that we'd like to transform the data in a space where the relationships between the variables are very simple, right? And so because they're going to be very simple, they're going to be very simple to learn as well. So, I mean, the extreme case of this is the most common assumption in many deep generative models is what we call marginal independence, assuming that in the right representation, all of the variables, all of the factors are marginally independent of each other. I think that's too strong of an assumption. Like most interesting variables, that the kinds of concepts we manipulate are not independent of each other, but the dependencies are simple. And they may be due to, for example, simple rule-like type of high-level knowledge that we communicate in language. Another thing that I've studied and I think is important in relation to causality is that the kinds of factors we tend to talk about in natural language have to do with how we can control the world or how other agents can change things in the world, right? So we like to give names to things that can be changed in a way that can be understood easily. And so this is a notion of controllable factors. And I'll mention the consciousness prior in a couple of slides. So one thing that helps understand where we are versus where we want to go is the distinction in cognitive tasks between what Kahneman and others call System 1 and System 2 tasks. So System 1 tasks are the tasks that we do using basically our intuition. We can do them really fast, and the way that we solve these problems are essentially heuristic. They're not perfect, right? And it's all happening at the unconscious level. We don't know how to explain how we do these tasks, and so it's not linguistic. And deep learning currently does really well at these kinds of tasks, but of course there are other tasks, like if I ask you to add two large numbers, you can do it in your head or using paper, and it's going to be slow. You're going to use logic, it's going to be sequential, and you can do it consciously and explain it linguistically. And this is what algorithms in computer science really are about. And this is also what classical AI was trying to deal with. Obviously, our brain is doing both of these things. In fact, most of the work is done by System 1. But we need the two of them, especially if we want to have machines that can interact with us in natural language. And so one of the things I'm going to say here as a recommendation for on the path towards AGI is we can't continue doing the kind of natural language research where we only train on text data. We have to build systems that simultaneously can understand words in sentences, but also what those words refer to in some environment. So this is called grounded language learning. And there's some work in that direction, but I think it's going to dominate in the future in the ability of delivering systems that can actually understand what the sentences mean. So recently, with a group of my colleagues at CFAR, we laid out a plan for the next 5 years about where we want our deep learning research to go next. Let me go through 4 of these points. One is, move the focus from passive observation to active agents, so basically agents. Of course, we've been doing reinforcement learning, but up to now it's been kind of a separate thing in machine learning conferences, and what I'm saying is, in order to move towards AGI, this is going to have to be part of a lot more of the research. And all of these points are related to each other. Related to that is, well, we have to go beyond perception, where we're already doing pretty well, to reasoning and planning, which are these things we're doing at the highest levels of representations that I've been talking about. And we have to do it in a way that allows the learner to develop a full but incomplete model of the world that captures causal structure. So we have a causal model of the world in our head, which allows us to do things like imagine situations that have never happened and will never happen, so-called counterfactuals, and allow us to plan and reason even about things that are unlikely. This is not something that current machine learning does well. And in doing all of these things, we want to continue on our path of getting inspiration and producing synergy with the research, trying to understand how humans are intelligent, so neuroscience, cognitive science, and so on. It's been very important for my work and many of my colleagues to drive our exploration of AI, and I believe that there's a lot more that we can gain. And of course, we can also give back to neuroscience and cognitive science with the models we're building to help them understand how the brain actually works. So to summarize, one of the things we want to do is joining System 1 and System 2 using grounded language learning, where we build high-level representations of what is going on, but that are anchored in low-level perception, and where the meaning of the words is not just like some word embedding, but it's also connected to actions and low-level perceptions. So one of the practical, like nitty-gritty questions on that path is, should we first learn a world model, think about like a baby which doesn't act in the world and just, or maybe acts in the world but doesn't speak, and doesn't hear language and just tries to figure out the physics of things. And then later, once we know how the world works, then we just tag words on these things and we learn a language model. Or should we do both things at the same time? So this is an interesting question, and my view on this is that we should do both at the same time, although of course learning the world model is like the primary thing that needs to drive things. If you think about babies when they're born, initially, of course, their knowledge of language is 0, and except they already know a bit about the sounds. And so the main thing they initially learn is about how things work in the world from a physical point of view, and how other human beings behave. Some clues that this is the right thing to do include things like, the fact that if you train with supervised learning these ImageNet classifiers, the representations you're getting, so forget about the classifier itself, but just the representations you're getting at the top hidden layer, are really, really good, and they allow to generalize to new categories that have been never seen. And if you think about it, in the case of these classifiers, we are using human knowledge of high-level categories by doing supervised learning. I mean, it's not like a complicated language. We're just saying the names of things, right? And so by doing that, we're actually getting representations that are much better than the representations we get if we do pure unsupervised learning, where we don't provide any labels. So providing labels is like providing a mini language to those learners, and it actually helps them discover better representations of the visual world. Right, so this is a clue that we really want to have not purely unsupervised learning, but eventually having language input to drive these what I call baby AIs. Okay, so part of this is how do we learn these models of how the world works? And I think this is going to be absolutely necessary to deal with the current problem of systems that can be fooled very easily. So there's also like a robustness and even safety issue with current systems. Think about self-driving cars being in a very rare and dangerous situation that has never been seen and is statistically unlikely. Current methods, I think, would tend to fail on these situations, but humans can imagine these situations even before they occur and learn to behave properly. And we're able to do that because, I don't know what happened with the title, but because we have good model of the underlying causal mechanisms. And this allows us to generalize in a non-trivial way. So traditional machine learning has been about IID generalization. So the training data and the test data are supposed to come from the same distribution. We've been living with this hypothesis for decades. But it's wrong. It's not like what humans do. It's not what the systems we build for applications actually need, because we train on data from, say, a particular country, and then we want this to work on another country. So that assumption leads to lack of robustness. And people have thought for a long time that, well, that's the best we can do. If we have that assumption, then we can get guarantees of generalization. If the test data doesn't come from the same distribution as the training data, then what guarantees do we have, right? Well, so what I claim is that we can get a more powerful form of generalization by relaxing the assumption, but still having some assumption that's just weaker. And the assumption is that the weaker assumption is that the scenario where we're going to be using this system it corresponds to a distribution that may be different from the training one, but involves the same causal mechanisms and the same underlying concepts, right? You can have the same underlying concepts and the same underlying causal mechanism, but the distribution is very different. Think about taking pictures here on Earth and then taking pictures on the moon. It's the same underlying physics, but we get very different looking pictures, right? So what changed is it's the same dynamical system, like the physical dynamic system, but initial conditions, maybe the gravity of the moon, is very different. And maybe also actions that agents take, like you intervene and you change things in the world, are going to change particular variables in that dynamical system, leading to potentially very, very different observation distribution. Okay, so how do we get there? One direction that has already been taken in our field, and I think is going to be, again, central to reaching AGI, is to use simulated environments, right? So why does it make sense? Even if our simulated environments are really simple compared to the real world, actually, I think we can learn a lot from that. And the reason is that this is like a subtle thing. We're not trying to build AI or AGI right now as like build the system that understands how our world works. It looks like that's what we want to do, but actually what we're trying to do in machine learning research is find the learning procedure which, if it was put in our world, could figure out how our world works, right? And we can test those learning procedures in simpler contexts that we can analyze and break down into gradually more complex requirements. And that's what I and others are proposing to do. So I think eventually we'll converge to some sort of benchmarks, which I think was Tegan proposed to call them AI Olympics, where different research groups would propose different environments where each research group would have to deliver learners that can deal with all of these environments, right? And you can think of this as a more sophisticated Turing test that we would grow the difficulty of these tasks as we make progress in research. So we've actually started this with a project called the Baby AI platform. And we found that even with a very, very simple environment, which is like a grid world associated with language constructions that have a compositional nature, so there's an almost infinite number of potential instructions of the form things like, navigate to this place and put something next to something else. The tasks currently are extremely difficult, even for the current best reinforcement learning and imitation learning systems that we have. So these really, really easy tasks that humans can probably learn 100 times faster need hundreds of thousands or millions of demonstrations to be learned. So in a sense, I mean, it's bad news in the sense that, we're really very far from AGI. And the good news is that means we can study those problems in setups that are simpler and easier to analyze, that don't require as much computational power. What else is missing? So if you think about how current machine learning and RL are modeling the world, I think in addition to the causality aspect, there are many other issues. So for example, our current typical model, think of predicting the future as a sequence of one-step prediction. Like I'm going to predict the next frame, and then given that and the previous ones, I'm going to predict the next one, and so on. So we typically have these decompositions by conditional probabilities of the next thing, and then the next thing, and the next thing. And that's not at all how humans build visions of the future, right? We can project ourselves at arbitrary points in the future. We don't need to have like a little movie in our head of all the intermediate time steps. We could say something like, tomorrow I will do this, and I don't need to predict all of the intermediate time steps. In addition, when I say tomorrow I will go to the beach, I'm just talking about the beach. I don't need to talk about all of the other aspects of the future state of what will, how the world will be tomorrow. And the world is extremely complex. It has maybe tens of thousands of interesting variables I could talk about in natural language. But I'm choosing to only talk about one or two or three in that sentence. And we do that all the time when we project ourselves into the future, planning or imagining or constructing hypothetical situations. So this notion of focusing on just a few variables at a time in our mental projections is something that's missing in current machine learning. And this is something I proposed last year in a paper called The Consciousness Prior, which actually considers that this ability that we have to talk about the world using just a few variables at a time is actually an important statistical advantage. And so that's the reason I call it a prior, because it's assuming something about the world. It's assuming that only looking at a few variables, like tomorrow it will rain, I can actually make statements that have a high probability of being true. This is very, very different from if I have to make a prediction about all of the pixels tomorrow. And if I were to try to make these kinds of predictions in the wrong space, in the space of pixels, for example, I wouldn't be able to make very good predictions. If I'm trying to predict one pixel given 3 other pixels, even if I pick those pixels well, it's not going to work very well, right? If I'm trying to predict how things will be tomorrow. But if I can talk in the high-level language of, say, it's going to rain tomorrow, I think it will rain, actually. Then I'm actually able to make these very powerful statements. And that's what we are exploiting when we say things about the world in language. This is also what classical AI was exploiting with the notions of rules and the variables that are associated with that. So now what this is saying is, in addition to this notion of finding the right space where we want to make those statements, we also need to learn those statements, which are those rules, right? And you can also think of them as the causal mechanisms which relate the variables together in a graphical model sense. All right, let me skip that. So because I use the word consciousness, and this is something that interests people here, let me sort of now sneak in my view on consciousness. So I think we're confounding, I mentioned it yesterday, we're confounding lots of different things that computationally are just different, they're related when we talk about consciousness. And none of those here include the notion of moral agent and moral patient, which is actually the notion that we care about when we say, oh, we what should we do if we have a conscious machine? Should it have rights and things like that? I think this is one aspect which has to do with social interactions and social contract. But really, there are computational aspects which can be studied separately and built in machines in ways that I don't think are so complicated. So self-consciousness is just having a notion of my state within the bigger set of my model of the world. Access consciousness is what I'm exploiting in the implementations of the consciousness prior that I talked about, where we only focus on a few things at a time, right? This is attention, and this is the things we're focusing on are these thoughts that we have at a particular moment. Emotions, well, emotions are just shortcut calculations to predict the value of some future state or expected value of future states in socially context-dependent setups. And those sort of predictions are very powerful for us. They influence what goes in our memory, the things we choose unconsciously to remember, and how our next action are going to be decided. And then finally, maybe the one that's the most problematic is the notion of subjective experience or subjective perception. And I believe this is an overblown issue. I think that even with current neural nets that learn to represent the world, what they have is actually subjective perception. Each of these neural nets is trained on different data and develops different representations of the world. So if you think about the color red, right? Well, for those neural nets, the color red is not the wavelength. It's these high-level representations of red things, which for some neural net may be associated with positive experiences, or for some other neural net maybe some negative experiences, and may be associated with particular aspects of the world that could be different from one individual to the other. Quickly, AI progress comes, and the path to AGI comes with all kinds of hopes and dangers. I don't need to maybe go through that list. Let me just mention a few things that we're doing at MILA. So we've been part of the work on the Montreal Declaration for the Responsible Development of AI, which you can think of as a more elaborated version of the Asilomar principles. There are 10 principles. Each of them has things like well-being, equity, diversity, prudence, responsibility. Each of them is then broken down into sub-principles, which I think go beyond just AI, but also the values that we care about, as was the case for the Asilomar principles. We're also involved in organizing workshops and events like the AI for Good workshop at the last NIPS, and we have an upcoming workshop on, or school, I'd say, on bias and discrimination in AI. One thing I really care about is we believe that it's important to democratize AI around the planet, and in particular, to make sure that developing countries can build their expertise in AI. So we have a program to bring in students, undergrad or grad, from developing countries like Africa and spend a few months at MILA. We have projects in, of course, applied AI in things like healthcare and now climate change. Let me mention one project which I find cool that we just started. And, because I think it's related to some of the issues discussed here about global governance and how to make people on Earth move towards the better collective decisions. So one issue with climate change is people don't really understand emotionally what the importance of this, because what we're seeing in the media and in papers is very abstract. It's happening 50 or 100 years into the future. And even if there's going to be hundreds of millions of people dying because of these things, it's hard to make it personal and emotionally grounded. And so what we're proposing is to use machine learning in a positive way, in an ethically correct way, to convince people of the importance of climate change in a way that's going to be emotionally grounded. So for example, we could use variations on GANs to present images of your house or of your descendants in 50 years or 100 years as a consequence of the current decisions about climate change. Last thing I want to mention, this is really my last slide. So this is a little bit more, I know many people might disagree with this here, but about existential risks. So I do think that AGI and AI in general comes with lots of risks. But one that I'm less confident about, less convinced of, is the risk of a really, really fast sort of exponential self-improvement once we reach AGI. I don't think that there's going to be like one cutoff point. Oh, we reach human-level AI, and then suddenly it sort of shoots off. I don't believe that. Why? So if the future AI is built on machine learning, and the kind of machine learning I understand now and I can imagine in the future, then the change, like the self-improvement, is not something that can happen very quickly. It's something that changes very slowly through learning, right? And by sort of gradient-based optimization. The other thing is learning involves actually diminishing returns in terms of the amount of knowledge obtained as you collect more data. So even if I multiply the amount of data by 1,000, I don't get 1,000 times sort of more efficient classifiers. In fact, you have a sort of exponential wall here that's well understood in learning theory, and similarly, so rather the competence probably grows something like log of the number of examples, and another clue is that the size of the brain doesn't seem to be such a big factor. Like even if we had a brain that was 10 times bigger, I'm not sure we would be sort of 10 times smarter. Consider the fact that whale brains are much bigger than ours, and I think the main difference between whales and us is that we have a culture, and that allows us to gather much more knowledge in the same size brain. And the other last point is, if you look at computer science theory and machine learning theory, you find many, many exponential walls. So the opposite of exponential improvement is basically things become exponentially hard as you try to solve some problems because of things like the curse of dimensionality and all kinds of exponential growth that make, for example, search exponentially hard as you consider harder and harder search problems. All right, I'm closing here. Thanks. I'm very surprised.
What'd you say?
I'm very surprised.
Oh. You talk about the diminishing returns of more data.
Yeah.
But I think that's actually when we're talking in this regime of IID data on a single task.
Sure, I agree.
And
If we have active learning, we can do a lot better, but we don't have really proofs that active learning, except in the simplest setting, can
but I'm not talking about active learning. I'm talking about multitask learning and horizontal transfer.
Yeah, but that's only linear. It's linear. Whereas the other
well,
one is
it's actually, I would argue, it's at least linear, which is much better than logarithmic, and potentially super linear because we see positive transfer right now when you train on multiple tasks. So I guess if you had an AI that was very competent on one task, I wouldn't be surprised if it could rapidly become competent on a whole host of tasks, for instance, everything that humans can do and more.
I agree, but I don't think you get the kind of exponential growth that people are afraid of. So, of course, I'm all for multitask learning. It's very important. Other question? I'm sure you do.
Thank you for your wonderful speech. And I have a short question and two questions. First question is consciousness player is a kind of access consciousness?
Yes.
And second question is, in this slide, exponential self-improvement is difficult, you think, but if the AI gets some kind of common sense, then they can program other AI. So in that case, there are some possibility to exponential. What do you think about it?
Well, humans are really, really bad at programming, actually.
Yeah.
So if we get human-level performance, ability, it still sucks in terms of the ability of programming things. So I'm open to demonstrations that I should be much more concerned, and I've already voiced that to a number of people, and I'm glad to engage in that discussion because I do care that we don't make tragic mistakes, but I haven't seen a convincing argument yet. That being said, I think that where there's a common ground between my view and many people here is that whatever we think about the existential risk coming from superintelligence, there's a large risk coming from abuse of AI from humans who could control it, and potentially even accidental destruction of people and wealth by people, and especially nefarious use.
Hi, you seem to insist on this idea of a spectrum of consciousness.
That's right.
Which I agree with. But don't you think there is a phase transition that could arise, like solid, liquid, gas, and then consciousness is maybe just like many different kind of gases, but is there a phase transition that is sharp and really a cutoff? Thanks.
There could be. Because I have decomposed consciousness in a number of aspects, and for some of those aspects I can see like gradual improvement, like you get better and better representations, or you can model more and more aspects of the world, or you can search more efficiently, right? So there are many ways in which you can get progress, and maybe some of these are like qualitative jumps. That's quite possible, yeah.
Thank you. We've talked about a number of these points, and so I really agree. But on the causality thing,
Yep.
So human intuition about causality is heavily linguistically based, and it's heavily from embodied senses of agency.
Yes.
Whereas, there's these, sort of mathematical causal graphical models
Right.
type of notion of
Causal
causality, which is not necessarily the same thing.
But they're closely
humans
related.
are not they're somewhat related, but humans are actually kind of bad at this kind of,
Right.
Kahneman, et cetera.
You're right. You're right.
So I'm wondering, maybe expand on which of these you mean where.
So we're bad because we're not good at search. But what we're good at is at figuring out the right variables. And those variables are the ones we're talking about, the ones we're giving names in language.
Great talk. I wanted to dive into one of the things you said earlier about the benefits of learning about the environment and learning language at the same time.
Yes.
You can get these higher level abstractions more quickly.
Yep.
Certainly seems true in like a shortcut. One of the costs might be that you learn the same abstractions that we know about.
Absolutely.
And my understanding is, for instance, when machines are learned to diagnose cancer from different images, they sometimes come up with new kinds of abstractions that none of us had thought of before.
Right.
So maybe talk a little bit about the trade-off of
Sure.
locking into our pretty good but not perfect set, and maybe there are other ones, especially since they have other senses that they might be able to draw on.
So I believe in gradual progress in science, and I'd be very happy if we have machines that already have our intelligence. And if you wanted to be more ambitious and have machines that have a lot more intelligence, then you might want to free them a bit more from the constraints, if you want, of our language and our culture. Although, keep in mind that these are not hard constraints. It's more like you're booted up with that knowledge, and now humans can discover new things, and those machines could discover new things as well. So we could explore both.
Unfortunately, that's all the time we have for questions right now.